Okay, Unit 13, test review. Given the functions f of x equals 10 to the power of x, 2 to the power of x, and e to the power of x, state the following. So they're all your parent functions. So all your parent functions are going to have your most basic attributes. So for instance, if I put 10 to the power of x here, 2 to the power of x here, and e to the power of x here, and I graph them, there's your 10 to the power of x, 2 to the power of x, and e to the power of x. So all of them, their domain will go from left to right, so negative infinity to infinity. Your range, you'll notice it doesn't go below the x-axis, so that's going to be from 0 to infinity. Or you can say y is greater than 0. The y-intercept is all at 1, and if you go look at your table, you'll be able to see that 0, 1 right there. So they all have a y-intercept of 0, 1. And because their range is restricted at 0, the horizontal asymptote will be y equals 0. Okay, on the next one. It can be a little confusing with all the letters, so what I'm going to do is I'm just going to put numbers in. So let's say this is negative 3 times 2, and then x minus 4 plus 5. So this a right here will tell me this. So what that can be is that can be your reflections across x. That can also be your stretches, your vertical stretches, and your vertical compressions. Remember, compression would be that fraction. Okay, on B, this is just your base, and it's just all about the parent function. So it really doesn't tell you what kind of transformations you're going to make. Okay, on C, this is your horizontal shift. So this is your left to right movement. So for instance, this one would move 4 to the right. This one here for A would be a reflection and a stretch. Now this back here would be your vertical. So that would be up or down. Okay, so on the next one, we're just going to state the transformations for the equation below. And this is going to be what our parent function is, similar to, again, this. So everything starts off with this. All right, so this one I see a negative, so I know it's going to be a reflection. This is just my base, so it doesn't tell me anything. It's going to move left 3 and up 7. All right, on the next one I see a half, so it's going to be a compression, vertical compression. It's going to move right 4, down 9. All right, this is my parent function, so I'm really only looking at this 7 right here. And this 7 tells me it's going to be a vertical stretch. And that's the only transformation I see. All right, on the next one, I do see that negative. So that's going to tell me it's a reflection across x-axis. The 4 tells me it's going to be a vertical stretch. The plus 1 is going to tell me left 1. And then down 3. Okay, on the next one, you're just really looking to graph it. So you want to find some good points. Now, it's always good to start with the, you can start with the y-intercept, and then also start off with the vertical asymptote. So if I put this right here, I'm sorry, the horizontal asymptote, horizontal. All right, 1, 2, 3. So I'm going to draw my horizontal asymptote, and I know that the graph cannot pass that. All right, so let me go type it in. Clear all these out. If I go look for some points, I'm going to put a point at 0, 4. I'm going to put another point at about 1, 5.7. So right there. And then what I'm going to do here is I'm just going to make sure that it goes along that asymptote and does not cross it. Okay, so for my domain, it's still going to be negative infinity to infinity. Now, because this is a plus 3, that tells me my graph can't go any lower than that. So my range from low to high would be 3 to infinity, or y is greater than 3. Okay, on the next one. Okay, all I'm doing here is I'm just matching them. And what I'm really going to focus on is I'm going to focus on the horizontal asymptote. So I know I have a horizontal asymptote there at 1. And if you notice here, this is 1 right here. Okay? And it also raises really fast. And I know anything to the, with a base of 10 raises really fast. So this one is going to be A. I'm going to look at the horizontal asymptote here at -2. There it is. -2. So this one will be B. And this one doesn't have anything, so I know it's a plus 0. So the horizontal asymptote is at 0, and that's that one right here. This is also a parent function, 2 to the power of x. So it has that y-intercept at 0, 1. All right, on the next one, I'm writing the explicit rule. Now, your explicit is going to be that a sub n equals r times, ignore that. That should be the a sub 1. A sub 1 times r, and then n minus 1. All right, so for this one, this is my a sub n, a sub 1. And then I notice that it's multiplying by 3 each time. So that's going to be my r. Okay, so here I'm going to write the rule. So a sub n equals a sub 1, which is 3, times the r, which is 3, and then n minus 1. All right, now I'm going to write the recursive rule. So the recursive rule still starts with a sub n equals, this time I just need the r though, so r times a n minus, sub n minus 1. And I have to also know what my first term is still, so 3. All right, on this one, I'm writing the explicit rule. So again, a sub n equals, the first term is going to be 8 times, and I notice it's halving. So if it's dividing by 2, that's the same thing as multiplying by 1/2. So multiply by 1/2, and then n minus 1. All right, if I write the recursive rule, that's a sub n equals, again, I want to start off with the 1/2 times a sub n minus 1, and I need to know the first term, so a sub 1 is 8. Okay, on the next one, I'm going to write an exponential equation. So first of all, I notice after each round, half of the teams were eliminated. So I know it's going to be decay. And then it says, representing the number of teams T that remained after R rounds. So this one would be T, the function of, see what the function of the rounds are. So here it starts off with 68. Then I'm going to do 1 minus, it says a half, so 0.5 to the power of R, which then equals 68.5 R. And again, I use the minus because it's decay. All right, on this one here, it says Lewis invested $2,500 in an account that averaged 2.5 interest per year. So it's gaining interest, so that's going to be growth. So if I write the equation, it'd be y equals the starting amount, 2,500, and then 1 plus because it's growth. Now you need to change this into a decimal, so 0.025 to the power of x. And then it says, how much money will he have after 10 years? Well, 10 years, your time, that's going to be your x, so x equals 10. So here, if I have 2,500, and then 1, I'm actually going to add that 1 in that 0.025, so there we go, to the power of 10. All right, so if I put that in my calculator, oops, I'm sorry, y'all. I couldn't tell if the camera didn't have that. Okay, so here I'm going to have 2,500, then 1.025 to the power of x, actually 10, and you get $3,200 and about 21 cents. Okay, all right, let's flip it. Okay, on this one here it says, last year, 2,500 trees were planted in the National Forest, but trees died So that's going to be decay at a rate of 4% each year. How many trees will there be in 7 years? All right, so for your equation, I know it's going to be decay because it says dying. So it starts off with 2,500 and then 1 minus. Again, you have to change that percent into a decimal. So 0.04 to the power of x. Now that would actually be, once I subtract that 1, 0.96 to the power of x. Now, my x here is going to be 10. So to do my answer, I'm going to do 2,500, 0.96 to the power of 7. So 2,500, 0.96, because 96% of the trees remain after the 4% rate of decrease, and then to the power of 7. So after 7 years, we should expect to have about 1,878 trees. All right, on the next one. On this one, pretty much, they're telling you what T is, so you just want to substitute in for that. So I'm just going to put that in here. So I'm going to do 15 times E to the power of negative 0.01 times 50. And I get about 9.1. I'm just rounding it. Okay, I'm going to do the same thing. I'm going to go up here. But this time I'm going to change that 50 into 75. And I get 7.0. I'll say 7.09 or 7.1. So about that. All right, on the next one, you're just matching. So if money is locked in a safe, y'all, it's not gaining any interest. You're not putting anything in it, so nothing changes. So it just keeps the value that it started off with. So what they're telling you is each of these start off with 173 of something. So this one would be B. Now, when you're using an inkwell, the ink is running out of the well, so that's going to be decay. So it has to be less than 1. So C. And this one, height of a young tree. You know, hopefully the tree does continue to grow, so it'll be a grow above 1, so A. All right, on the next one it says, on tax returns, self-employed people can depreciate the value of business equipment. Suppose a computer valued at $2,000 depreciates, so that's decay, at a rate of 30% each year. How long will it take for the computer to be valued at $350? So I'm going to write the equation, so Y equals 2,000. Again, it's decay, so 1 minus 0.30. To the power of x. Now, I'm actually going to put this one in my calculator because I want to see about when it turns into 350. Okay, so I'm going to do 2,000 because that's the original amount. And then this would actually be 0.70 once I subtract it, so 0.70 to the power of x. And I'm going to go to my table, and I'm just going to kind of look around, and I want to see about when it becomes about $350. So you'll notice here it's about 5 years when it comes to 336. So somewhere between 4 and 5 years. All right, on the next one we're just looking at the transformation. So again, this number here is just your base. That just tells you which parent function you're dealing with. This is what's going to tell me about my transformations. So I know just from the transformations that it went left 5, and I also know it went up 3. All right, your domain for these, unless it's going to be restricted, is going to be negative infinity to infinity. This is your horizontal asymptote. So for your horizontal asymptote, it's y equals 3. Your range is also about your y, so it tells me this is the lowest it's going to go. So 3 to infinity. Or I can say y is greater than 3. Okay, and then for the y-intercept, what I'm going to want to do is I'm going to want to substitute, and I'll do this one by hand. So if I substitute in 0 for the x, because that's how you find your y-intercept, I'm going to get 10 to the 5th power. Okay, so 10 to the 5th power. And then if I just add 3 to that, I'm going to get 0. So I'm just adding 3. And that is my y-intercept. All right, on the next one, again, transformations. We're just looking here. This is the parent function. So as far as my transformation go, I'm just looking here and I'm looking here. Nothing's happening here with the horizontal, so it's not going to move left and right, because there's just really like a plus 0 or minus 0 there. But what I can tell is this is going to be a vertical stretch. And I also know it's going to move up 5. All right, your domain again is always negative infinity to infinity. It's always going left and it's always going right. This is my horizontal asymptote. Okay, so because that's the horizontal asymptote, that's going to affect my range. The lowest it's going to go is 5, so 5 to infinity, or y is greater than 5. All right, for the y-intercept, same idea. I'm going to do this one by hand also, so 5e. I'm going to put a 0 there, plus 5. Okay, anything to the 0 power is 1. 1 times 5 is 5. 5 plus 5 is 10. So 0, 10. You can also put these into your calculator and look it up that way. So for instance, if I came here, I would do 5 times e to the power of x plus 5. And if I go to my table, it's 0, 10. So same thing. You can do it either way. All right. All right, on this one here, we're doing a geometric sequence. And I just want you to make sure you know each of the parts of the explicit. So here I can tell my starting value is 6. It's going to be multiplying by 2, so that's my common ratio. And then they want me to find out when it's 5, what the fifth term would be. So here I would do 6, and then 2, and then 5 minus 1. That would be 4. And again, if you wanted to, you could just put it in your calculator like this. So 6 times 2 to the power of 5 minus 1, and that would give you 96. All right, this one here I'm actually just going to kind of look at as growth and decay. So I'm going to ignore all that. So a particular bacteria divides in half. So remember, y'all, if it divides in half, it's a little bit different with bacteria and stuff, because that actually means there's becoming more and more. It's kind of like mitosis, you know, like when cells start splitting to make something larger. So a scientist begins with 20 bacteria. So y equals 20. Write the explicit and recursive rule. Again, we're going to look at this more of growth and decay. But we are going to determine how much bacteria exists after 4 hours. So y equals 20. It's going to actually be doubling, because I remember as it's halving, it's actually becoming more and more, twice as much. And then I want to know for every 20 minutes. Now this can get a little confusing. There are 3 20-minute sections in an hour, okay? And then 3 of these 20 minutes is an hour. And then times 4 would be 12. So 20 times 2 to the power of 12. So if I work that out, equals 81,920. Okay, on the next one, and I'm only going to do one of these just because you should be able to do this. We've been doing recursive since Algebra 1. All right, so what I'm going to do is I'm going to go to my table. I just did stat edit. And I'm going to, first let me clear all this out. Okay, and then I'm just going to start putting everything in. So I've got 4, 5, 6, 7. And then over here I'm going to put in 120, 168, 235, and 330. Okay, now it tells me to do an exponential regression. So stat, calc, I'm going to go down to 0. That's my expreg, exponential regression. And I'm going to see about what my equation would be. Okay, so there's my equation. So if I write my equation, I'm going to round it. So I'm going to say y equals 31.15, I'm going to round to the hundredths, times 1.4, put that in parentheses, to the power of x. Now here they're telling me that the x, because remember this is like f of x, is going to be 9. All right, so if I go to my calculator and I type in my equation, I can tell it's growth also. It's growing by 40%, okay, because it's greater than 1. 0.4 is 40%. And if I go look at my table, I'm going to look at 9. Okay, so I'm looking at about 643 deer. But then it says, how many deer would you expect to be in the population the year 2014? Well, this started off at 2,000, so that'd be 14 years later. So if I go down to 14, about 3,461 deer. And then it wants to know 2020. Well, again, since 2000, that's 20 years. So 26,063. And again, on this one, it's just, stat edit. On the next one here, just stat edit. All right, this one you're talking about the type of function. So what you want to do is you want to look for your patterns. So this one, just kind of looking at it, I quickly noticed that it's just adding by 2 everywhere. So when it's just adding by 2, that's going to be linear. And we call that a common difference. The difference in the numbers is that it's adding by 2. All right, on the next one, I can tell that it's going down. And it looks to be dividing, which is the same as multiplying by 1/2. Let me see if it keeps doing that. 10 times 1/2 is 5. 5 times 1/2 is 2.5. So this is actually going to be exponential. And it's because of the common ratio. All right, on the next one. Okay, so looking at it right away, I don't really see a pattern. I know it's kind of going up, but I don't see anything solid. So I'm just going to kind of look at it. I can tell that's doing +4. Then that did +6. And then that did +8. And I'm still kind of like, oh, wait a minute. Now I'm noticing that this is going up by 2. Going up by 2. So notice I didn't look at what was happening here. I looked at what's happening here. So that's actually called a quadratic. And that's going to be your second difference. Okay, so that should be it. If you have any questions, make sure you ask your teachers. And good luck. Please study.